Hello, my name is Gedaliah Knizhnik, and I will be presenting the paper, Pauses Provide Effective Control for an Underactuated Oscillating Swimming Robot. In this paper, we tackle the challenge of designing closed-loop control for an inexpensive swimming robot capable of modular self-assembly. The core of our robot design is provided by Rafael Ndegani, who adapted the concept of internal rotor propulsion to aquatic robots. This actuator, which uses only one motor and passive flippers, allows one actuated degree of freedom to move the system in a planar space. The simple design and single motor trades ease of control for simplicity and low cost. The long-term goal of our work is modular self-assembly, turning teams of individual robots into capable structures. While significant work has been done on this for terrestrial robots, there is very little exploration of it in the literature for aquatic systems. It has been done before by O'Hara et al. And Paulus et al. In the TEMP project shown here, but holonomic motion was taken as a prerequisite, so the individual unit robots were complex and expensive. This means that the teams employed were small, in the tens of units, but inexpensive robot units could allow this concept to expand significantly. In our previous work, presented at UR2020, we modified Rafael Ndegani's original design to make it capable of modular self-assembly. The top body, which functions as a driving mass, is expanded to provide a surface other units can dock to. The flippers are sized to reside within that footprint, which prevents mechanical interference between neighboring units. This allows, at least in theory, the robots to dock together to form a unit while maintaining the active structure and low-cost design. Now we have an inexpensive robot, and it's capable of modular self-assembly, but we have no real idea how to control it. Therefore, we developed a unique control methodology to leverage drift and inertia into sharp turning maneuvers. In our previous work, we considered the equations of motion for the Cartesian coordinates x and y and for the orientation theta. It turns out, however, that the equation for orientation, shown here, is independent of the boat's position, which leads us to consider it independently. While this opens the door for steering control, the equation is nonlinear and therefore difficult to use. So we define a discrete model to simplify our analysis. The motor angle phi oscillates in order to propel the boat. This causes the boat to oscillate, and each stroke, which we define as a rotation in a single direction, injects angular momentum, which is the first term on the right-hand side. A full cycle, or back and forth, which is 2 strokes, injects some net angular momentum. If we discretize by cycle, we can define the overall orientation as a summary orientation. For our purposes, the average orientation, as defined here on the right, and overall angular velocity as the change in the overall orientation. Then each cycle acts as an overall angular acceleration, alpha, with some unknown map from the motor input to that overall acceleration. So our nonlinear system is now a linear, discrete double integrator. So now we have a model for how the boat moves, and an idea that we should be steering it. How do we steer? Rafael Ndegani proposed using a cosine that is piecewise in frequency, as defined here. Because each half of the rotation occurs at a different angular velocity, each will impart a different amount of angular momentum, and is roughly equivalent to a differential thrust arrangement. In this example plot, we start with a symmetric wave in blue, then lower the period of the downstroke in red, then of the upstroke in yellow. It is not particularly easy to determine the relationship between the periods of rotation and the output steering, so we implement control in this mode by making several simplifying assumptions and applying PID as a general control strategy. First, we assume that the initial set of inputs is symmetric and that the total period should remain constant. Then we can calculate the difference between the two half periods using PID control on the overall orientation and apply it at the start of each cycle. As we will show later in this presentation, this results in functional control, but the differential thrust arrangement is slow to correct errors in orientation. In this work, we propose an alternative motion primitive. Angular drag is low for our cylindrical robot, which means that we can drift with relatively little loss of angular momentum. This means that if we insert a pause into our waveform at its peaks, we still end up with whatever change in angular momentum we would have had, but with an added change in orientation from the pause. This is effectively an energy-free rotation method that costs us time instead. The waveform defined here uses the previous definition for phi from the frequency control, but inserts a pause at a time specified by TPS and for a length specified by TPL. For control purposes, however, we would limit TPS to a binary choice of either 0 or T1/2, which is either the peak or the trough of the wave. We still don't have a map between the control inputs and the output, but we can simplify things by assuming, again, a symmetric base input so that the rotation comes only from pausing. For a fixed base input, we now have effectively one control variable, the pause length, if we let the sign signify the binary pause location. This one-dimensional control space is much more manageable, and we ran open-loop tests for a range of values and were able to numerically fit a relationship to the data, which defines how much the boat will turn per cycle for a given input. That means that our double integrator can be simplified further into a single integrator, with the controller defined in this figure. So how do these controllers stack up to one another? We heuristically determined a suitable base input, a symmetric wave with period 1.5 seconds and amplitude 2 radians, which balanced being fast enough to produce thrust, but not so fast that the motor couldn't keep up. All experiments described in this work used this base input. We evaluated our controllers by tasking them to respond to step inputs of either close to 0 or ± 90 degrees. In the plots here, you can see the collected responses across all the inputs, with the pause controller on the left of each plot and the frequency controller on the right. In the left graph, we plot the rise time, and you can see that the pause controller achieves the desired set point significantly faster than the frequency controller. In the middle, we plot the distance traveled during this rise time, and you can see that the pause controller travels much less, resulting in much sharper turns. It is also important to highlight that because these plots show inputs of both ± 90 degrees and close to 0, the tighter boxes for the pause control demonstrate that its performance is independent of the actual input. This is not true for the frequency control, which understandably takes longer to respond to larger errors. To illustrate this visually, we captured video of the mod boats performing 90-degree corrections. In both videos, the desired swim direction is to the upper left, parallel to the rails. The frequency controller, on the left, takes a long time to respond and correct the swim direction. The pause controller, in contrast, corrects sharply and almost instantly. You can see that while the pause controller has long since achieved its desired orientation, the frequency controller is only now traveling in the correct direction. We took this evaluation one step further by testing trajectories, approximated as a series of discrete waypoints. For each trajectory, the desired heading is given by the orientation from the mod boat to the center of the waypoint. The trajectory resulting from the pause controller is shown in blue, while the frequency controller is in dotted red. You can see that, while both controllers succeeded at the given task, only the pause controller followed simple paths from one waypoint to the other. The curved trajectories that result when frequency control is used demonstrate that the boat is struggling to achieve the desired heading. This is further clear in the heading plots for the square trajectory. Observe that the pause controller clearly approaches and maintains the desired heading, while the frequency controller lags consistently. Moreover, the frequency controller's inability to respond sharply results in the desired heading varying significantly as the boat drifts off course. The pause controller, by contrast, shows a consistent desired heading as it follows the expected path. I'll close with an experimental demonstration of the mod boat's performance while under pause control. The superimposed waypoints are approximate, but you can clearly observe the sharp change in direction that occurs when the next waypoint is targeted. Achieving similar performance with frequency control would require large areas for maneuvering, and the waypoints would need to be much further apart. We hope to use this kind of control to facilitate the placement of marine sensors or to patrol a region of interest for repeated measurement. In conclusion, we've shown that while the frequency-based motion primitive for steering the mod boat works, it shows slow rise time and requires large distances to maneuver, which makes it ineffective in precision applications. Pause control, by contrast, allows for fast and sharp changes of direction and is far more capable. By using this control primitive, we have been able to hit waypoints about 20 centimeters in radius, placed approximately 1 meter apart, and hope to improve this performance in future work. In other future work, we aim to use this control method to allow the mod boats to self-assemble into floating structures. Thank you for watching, and please reach out with any questions that you might have.